The number of times airplanes have struck birds has increased approximately linearly from 2.6 thousand strikes in 1992 to 10,000 strikes in 2011. So we're all aware that that's an issue for airports and airplanes, right? They're particularly most vulnerable right when the plane is starting to take off, and if a bird goes into the engine, right, the jet engines are sucking in all that air. If a bird goes in there and messes with all the mechanics inside, it could render the engine inoperable, and if they don't have too much altitude at that point, it could really cause some trouble. I think it's a leading cause of plane crashes, so it's a really important issue. Not a lot of airports do a bunch of things to try and prevent it. So to try and keep the birds away from where the planes are taking off, right? So they've tried, certain kinds of alarms to, get the birds to go away, scarecrows, and all kinds of technology has been developed to try and keep the birds out. But still, from time to time it happens, and as we see from this information, it has been increasing a lot, from 2.6 thousand strikes in 1992 to 10,000 strikes by 2011. So just looking at those two numbers on their own, 2.7 thousand and 10,000, would we conclude that we're doing a terrible job of keeping the birds away?
No.
No? Why not? What's missing in that statement? Or what's another part of the puzzle?
How many planes are flying?
Yeah, how many planes are flying. So if you're just looking at the 2.6 thousand and the 10,000, you might think that we're doing a terrible job. But also the number of flights has probably increased pretty dramatically from 1992 to 2011. So that might be part of it. Another part of it is not really telling you where they are happening. It might be like regional, right? It might be a really big problem in some corner of the country or the world or wherever this is. It may not be spread evenly throughout the, we don't know. But at any rate, all we have is these 2 points, and we're going to do our best to estimate or create a model for this situation just based on those 2 points. But we recognize that it's not necessarily going to be a great model since we have very limited information. Okay, so we're going to let n be the number in thousands of bird strikes in the year that is t years since 1990. Remember that in this class, we never use the calendar years. We got to convert it into a t value. So we convert those 2 years into t values. 1992 would be what t value? 1992 is how many years after 1990? 2. And 2011 is what t value? ...2011 is how many years after 1990? 21. Okay, so we got the t values of 2 and 21, and the number of bird strikes at 2.6 thousand and 10,000. So we can use those 2 points to create ordered pairs. So we can get a little table going, like this one, right? So now we have a table where 2 represents 1992 and 21 represents the year 2011. We have to be careful about that representation of t, because when we go back and answer some questions, we got to be able to convert the t value back into an appropriate year. Okay, so if we graph those 2 points, really roughly speaking here, we end up with, here's y, here's x. Let's say this goes in 2, 4, 6, 8, 10. That 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay, and in this direction, 2, 4, 6, 8, 2, 4, 6, 8, 9, 10. Okay, so roughly we'd say, oops, we went back to x and y. We want to use n there and t there, where t is the number of years since 1990, right? So this is 1992, 1998, 2002, 2004, right? 2010. Okay, so now we have 2 points. 2 comma 2.6 is going to be somewhere around there. And then 21 comma 10, that's going to be roughly somewhere over there. Right? So we have 2 data points. It'd be great if we had a lot more data points, but all we got is 2, so we got to do what we can with what we have. So we're going to draw a line to connect those 2 points. So we're going to stretch this out this way, and pretend that's a straight line there. And stretch it out that way. So that's what we're after. We're after the equation of that line that goes through these 2 points. Well, that's something we've already practiced a lot. We know how to find the equation of a line given 2 points, right? So there's really nothing too dramatically new in this question. It's just that is originally presented wrapped up in this word problem. So you have to practice extracting the information that you need. So this point is the point 2 comma 2.6, and this point is the point 21 comma 10. So, going back to the previous chapter, if I said, given these 2 points, find the equation of the line, well, by now that should be pretty easy, right? So whenever you see the words, or whenever you're after the equation of a line, you should think of y equals mx plus b, right? That's your standard equation. Okay, now in this case we're using different letters, so instead of a y we're using n, instead of a x we're using t. So it's n equals to m times t plus b, where we're after the m and the b. Our goal is to find those 2 values. If I can find those 2, I'm good to go, right? And we have 2 points. So the m is going to be equal to 10 minus 2.6 and 21 minus 2, which gets me to 7.4 over 19, which is pretty close to 0.39. Okay, so that's the slope of this red line. Once we have the slope of the red line, we can plug it back into there and get n equals to 0.39 t plus b. And now what do we do to find b?
Plug in points.
Plug in one of these 2 points. It doesn't matter which one. So let's use this one for instance. This is a choice of x and y. So we have to find the equation of the line such that when I plug in a 2, the answer is 2.6, right? We're looking for the number that makes this a true solution to this equation. So using that point, we can get 2.6 is the answer when 0.39 and this guy is a 2 plus b. So we multiply those 2 together, we get 0.78 plus b, 2.6, and we subtract them, and we get, what, 1.82? Yes, 82. 82 equals to b, and now we have all the elements we need. Here is our y-intercept, our b, and here is our slope. So now I know that this equation right here is is n equals to 0.39 t plus 1.82. Any questions? No? No? Okay, once we have the equation of the line, now we're able to make guesstimations about future values, what's going to happen in another calendar year, or something that happened in the past, prior values. Values that are between these 2 are interpolation, so maybe we're a little bit more confident that they would be accurate because they're between known data points. And then guesstimations using this part of the line or using this part of the line are extrapolation, and we're a little less confident since it's not between 2 known data points. But even the interpolation ones are probably not too confident since we only have 2 points, right? If we had a lot of points, then I would be very confident that that is the pattern. But if you're just looking at 2, then it's hard to say that that's really representative of everything that's happening. But we do what we can with what we have. So it's our best model given only 2 points. Any questions? No? So these kinds of word problems should be pretty straightforward. They just are, finding a way of giving you two ordered pairs. Find the equation of the line given two pairs. It's just that it's all wrapped up in this sort of word problem that you have to decipher. Don't forget that the calendar years need to be converted into t-values. And then you got to choose your independent and dependent variables. Very, very often in this book we use years. So very often t, the number of years from a starting point, will be the independent variable. Not always, but very, very often. Okay, good, good, good. What if, I don't know if it asks you this, but so what if we wanted to use our model? Our model is this red line, and we have the equation to be able to predict how many bird strikes there were in 2016. How would we do that? Find the number of bird strikes in 2016. Find, or I should say estimate, or approximate. Estimate the number, is this, of in 2016. Okay, how do we do that? How do we do that?
Substitute the t
Substitute the t with what?
with the t that represents 2016.
Which is going to be 26, right? T is the number of years since 1990. So 2016 is going to be at a value of 26. So on my picture, I really want to go out here, 24, 26. I want to go there. So this is 26. This is going to represent 2016. And I really want to find that and then go across and figure out what it is so that I can get a good estimation based on my model. Okay, so we have the picture. We could try and guess from there, but it won't give you a very accurate answer, right? So it's better to use our equation. So we're going to replace our t in this equation with a 26 and get a result for n. So n is going to be equal to 0.39 times 26 plus 1.82. And what do we get? $30 people with a calculator.
11.96.
11.96?
Yeah.
Okay, so 11.96 bird strikes. Right? Is that a good sentence for this? According to my model, in the year 2016, there were 11 bird strikes. 11.96 thousand, right? So pretty close to 12,000. The mathematical answer can be very precise, 11.96. But keeping in mind, going back to the fact that we only have 2 points, how confident am I that this is a exact and precise answer? Not really. So, I would say this is pretty close to 12. I would just approximate it to 12. And I would say, according to my model, there were approximately 12,000 bird strikes in the year 2016. About that. Okay, good, good, good. So it depends, pay attention to how much precision they want in your answer. We want precision because we want to confirm that you did it the right way and that the process is right. So the way we confirm the process is by showing the accuracy that you got. That's how I know you did it the right way. But in terms of just sort of stepping back and looking at the word problem, how do we really need to put that much precision? Putting that much precision implies confidence, 2, 3, 4, 5 decimals out. It implies that you know exactly what's going to happen, but you really need to step back and consider the fact that you only have 2 points here. This is not a very accurate model for that reason. And the other reason why it's not a very accurate prediction is because 26 is it's on the outside, so it's extrapolation, right? It's not between known data points. So I'm less confident about the results that are way out there and farther away from the last known data point. You know, maybe the pattern changed. Maybe this was a linear pattern from the 90s and the 2000s, but maybe starting in 2011 or 12, maybe something changed. Maybe the pattern changed in one direction or the other, and maybe this turns out to be a bad guess. I don't know. Good? Good? Yes, questions? Okay, so you can all Google to see how many bird strikes there really were in 2016, and we can figure out how close this approximation came to the real thing. Good? All right. How about this example? The number of Apple stores are shown in the table for various years. Let n be the number of Apple stores at t years since the year 2000. Find an equation of the line that comes close to the points in the scattergram of the data. Okay, so we look at our table, we look at our data. It states that in 2003 there were only 51 Apple stores. 2005, 95 Apple stores. So on and so forth. By 2012, 358 Apple stores. Okay, so the first thing we have to do is massage our data, right? Because we need it in a form that's functional for us. We never, ever use calendar years in this class. So we got to convert those years into t-values. So it says stores at t years since the year 2000. So they're letting us know what they want the t-value to represent. So the first thing we have to do is convert them. 2003 can translate into t-value of 3, and then 2005 into a t-value of 5 and 7 and 9, okay? So we convert them all, we get a new table, and from that new table we can graph those values, the t-values and then the, let's say n for the number of Apple stores. So we have a bunch of ordered pairs, we can graph them, we can get a scattergram from that. Okay, so let's practice with our calculator, graphing those ordered pairs to get that scattergram. This is the information that we want to use to create a scattergram with our calculators. So let's go to our calculator. Remember, we turn it on, this button down here, turn it on. Clear whatever's on your main screen, or quit to get out of wherever you might be. So quit and clear, get to this screen. Okay, first we have to input our data, so let's go to Stat. And then edit, hit enter. And then we want to clear some of these things. I want to make room for my new information. And I don't need any of this old stuff. So I'm going to highlight the L1, hit clear and enter to erase everything underneath it. Highlight the L2, hit clear and enter to erase everything underneath there. That's all I need for now, just 2 lists. I'm good with that. So what's the first problem here? What if I did that? Well, first of all, that's not, let's do that. What's wrong with that? Not a t-value. We never, ever use calendar years here, so you're going to get a wrong answer. You don't want to do that. Okay, so we got to convert our calendar years, right, these guys, into t-values, and the exercise told you to let t be the number of years since the year 2000. So this is going to translate into a 3 for 2003, and then a 5, then a 7, then a 9, then an 11, then a 12. Okay, those are the t-values we have to use to get the right answer. Okay, so I put those onto list 1. On list 2, I'm going to put the store numbers. So 51, 95, 169, 249, 321, and 358. Okay, there they are. Okay, so make sure they match in length, otherwise you made a mistake. Okay, these are going to be our ordered pairs, so they have to match in length. Okay, next we go to y equals, and see how there's an equation on there? It's going to cause a problem. I got to clear anything that is here. We'll learn more about this screen in a little bit, but for now, just clear everything. There's other things you could do, but for now, let's just clear everything. Okay, there's some down here, so They kind of sneak down there, so use your arrows to go down there. Okay, next we go into stat plot. So second, stat plot to get to this screen. And from this screen, I can tell, it's a nice little overview, that plot 1 is on. It's a scattergram because it's got the little dots there. L1, L2, that's exactly what I wanted. So there's really no need for me to go in there. But if you need to change something, then hit enter. And you get to this screen, on, scattergram, L1, L2. Now this is whether you want to graph little boxes, little plus signs, or little dots. So little plus signs, it doesn't really matter. Choose your favorite. And then again, if I go to second stat plot, from this screen I can tell that plot 2 is off and plot 3 is off as well. So I'm good to go. All right. Next, I got to go to my window. And this is the trickiest part of this whole thing. We have to tell our calculator which part of the rectangular grid we want to look at so that it captures the information we want. And this is guided in part by the ordered pairs I want to graph. So I know that the input values range from 3 to 12. So 0 to 20, I guess that could do it. That's not bad. But if I did something like 0 to 100, it might not look very good because the largest number is 12 and I'm going all the way out to 100. I'm going to have a lot of blank space. So you don't really want to do that. Right? It just takes a little bit of practice to kind of come up with good values. Let's just go to 20. That's fine. What about the y values? They're going from 0 to 1,200. It'll capture the results. Look, the range we're looking at goes from 51 to 358. So, I don't know, maybe to 500 would be good, from 0 to 500. Now remember, scale is the little tick marks. How do they count? So right now they're counting off by 2s. So this will go 0, 2, 4, 6, 8, 12, right? And this one's counting off by 5s. 0, 5, 10, 15, 20, 25. Okay, and that's going to count all the way to 500. That's going to be a lot of little tick marks. Right, so rather than 5s, let's count it by 50s. 0, 50, 100, 150, right? Okay, so when we're done with that, let's hit graph, and we get that. So remember, this guy was 50, 100, 150, 200, 250, right? That's what that was counting, all the way up to 500. And then over here, this guy was counting from 0 to 20 in multiples of 2. 2, 4, 6, 8, 10, 12, okay, all the way out to 20. So as you can see, just to play with it, look what happens when I change the y maximum to 100. We end up with the graph that just looks kind of ugly. This goes all the way out to 100, but our information, our input values, the largest number was 12. So I'm just squeezing all my points into this little segment over here, and it makes it hard to see. Okay, same thing if I went to the negatives. If I went to y minimum as like negative 100 graph, well, now this is starting all the way over here at negative 100. This ends at positive 100. And I'm really squeezing all my points into this little tiny space right in here. It just looks really ugly. Okay, so there's various good answers for the selection of your window, but also some not so good answers. Okay, so let's go back to writing it as a 0 to 20 graph, and it looks like that. Okay, so now the next thing we want to do is use this information, the scattergram. Now that we've got a scattergram, we want to use the scattergram to pick 2 points such that if I found the line that connected those 2 points, that line would make a good approximation of all the points. Okay, so you have to look at them all and think, well, what would make a good approximation? Would it be this point and this point, this point and this point? There are various choices that you can make. Now you wonder, well, how do I choose which is which? Remember, you can choose select the button that says trace, and then the little blinking cursor will let you know what value you're on. So that one is selecting 3,51 right now. We can use the arrow button to skip around. The next one is 595, 7, 169, and so on and so forth. So pick 2 points that would, such that when we find the equation line that connects those 2 points, they would make a good approximation. So for instance, let's use, well, I'll let you guys pick one. So go through and pick a couple of points. Once you've chosen 2 points, then you go through the standard process of find the equation of the line that connects 2 points. Okay, so we got our table information that was originally given to us. We converted the years into t-values. We got that. And then we created a scattergram. Scattergram that looked like this. Now the next step is for you to choose, based on this graph, for you to choose 2 points such that when you envision the line that connects the 2 points that you select, that line makes a good approximation of all of them. So kind of keep in mind where the pattern seems to be growing like up and to the right. So the line we choose should sort of be growing in that direction. Ultimately, we're going to be using that line as a model of this situation and use it to try and predict in values on information we don't have. Right? We already have the actual store numbers for various years, but there are various other years where we don't have information, and we'd like to use this model to be able to predict that, right? Like ultimately, we'd like to be able to predict how many Apple stores there'll be next year, or 10 years from now, or maybe in the past. How many were there in a certain year where we don't have information? Okay, so there's lots of good choices in this case, but there are sometimes bad choices. So maybe it's a little hard to see in this case, but for a second, let's pretend that our grid looks something like this. We have this dot, and 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 this dot. Let's say that looked like this. What would make good choices? Which ones would be good points to choose to approximate them all? So for instance, if some student chose, very often, most common thing people like to do is the first point, right, along the x-axis, the first point, and the last point. Alright, does that look like it would make a good approximation of all the points? Is it sort of in the middle of all of them? It's sort of the average of all of them? I don't think so. I mean, there's nothing above it and there's a few points underneath. It feels like it should be somewhere lower. So maybe, I mean, I would guess maybe the last one and this one, or this one, make a better guess. How about this one and this one? If I find the line that connects those 2 points, that seems to be a pretty good approximation, right? So there's several good ones. I'm not going to say that this one is better than that one. I don't know. They're both pretty good. You can choose either one. Maybe this one and that one. Maybe you think those 2 are pretty good guesses, right? So lots of good guesses, but certainly some bad guesses. How about this one and this one? That's a terrible guess. This point and this point, draw that line. That's not going to give you a good approximation of what's happening with the points. Neither are these 2. That's a terrible guess too. So are these 2. That's a terrible guess, right? Oops. So are these 2. These are also bad guesses, right? So there's lots of good guesses, but there's also lots of terrible guesses. Now back to this case, well, they're very, very close to a line. They're giving you a softball here. They're very, very close to a linear line. So there's really almost all choices are pretty good. Maybe only one of them is not as good as the rest. Which do you think is not as good as the rest? Using the first 2 points, maybe? Consider this. If we use the first 2 points and drew the line, we'd get that red line. Do you see how it's just veering lower than the rest of the points? I don't know that I would be comfortable using the red line to approximate stuff in the future, right? It seems to kind of be going too low. I'm going to underestimate what's happening. And then over in the other direction as well. So the first 2 are probably not a great choice. It's not as obviously wrong as some other cases might be. But the green line seems to be doing a better job, right? It seems close, a few points below the line, a few points above the line. It's pretty close. Maybe something a little closer to that one might be a better selection. So really the first 2 points is the only poor choice you could really make, or the almost every other point is, I think, superior. So pick 2 other points, not the first 2, and find the equation of the line. So for instance, how about 9, 249 and 12, 358? If If we choose those 2 points and draw the equation of the line that goes through those 2 points, that'll give me something that's a pretty good approximation of the rest, right? So if you already chose 2 different points, that's fine. If you haven't done so yet, then work with that one. 9, 249 and 12, 358. Okay, so this essentially boils back to the skills from the previous chapter. Find the equation of the line. Just like the previous example as well, it all goes back to y equals mx plus b. Everything in chapter 1 and 2 can be solved by that, with just a little bit of finessing. For one thing, we're not using x's and y's in this example. We're using n instead of y, and we're using t instead of x. But we still need to find the m and the b. That part has not changed. Okay, the m is the slope. We got 2 points. The 2 points we chose. That's the part that's different from this problem. They gave us a bunch of them, not just 2. They gave us a bunch of them. We needed to create our own scattergram so that we can choose which 2 points we would like to use. So we first of all have to find the slope m. So that's going to be y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And so we can label these. Let's call this x1, y1, x2, y2. And so this would be 358 minus 249 divided by 12 minus 9. Okay? And so we get 109 divided by 3. Which is
36.3.
36.3333.
Yeah.
Right, 3, let's just go out to 2 decimal places, 3. Okay, now that we have the slope, we go back to our formula. So now we know that n is equal to 36.33 t plus b. And now we use one of the other 2 points. It doesn't matter which one you use. So let's use the 9, 49. So we get 249 is the answer. 36.33 times 9 plus b. So now we multiply these 2. We get 326.97 plus b equals to 249. Subtract that onto this side and we get negative 77.97 equals to b. And now we got everything we needed for a linear equation. That guy is the intercept. That guy is the slope. And so our equation is going to be n equals to 36.33 t minus 77.97. Good? And in terms of x's and y's, we need to do that if we're going to put it back into our calculator. So y equals to 36.33 x minus 77.97, right? So it's the same thing. We're just saying that the y is, the n and the y are both the dependent variable, and the t and the x are both the independent variable. So this is in terms of our word problem, using the variables of our word problem. But then in general, it's x's and y's this way. And we just need it this way because our calculator only works with x's and y's. So to plug it back into our calculator, we would write it this way. Okay? Good. All right, so let's put it in our calculator. All right, so we were able to create our scattergram. There's our scattergram. And then we use the trace button right here to be able to move around. Okay, you know how this thing it's kind of in the way there? Once I wrote this, it's kind of blocking this guy. So what I'm going to do to fix that is to go over to the window, and I'm going to change my y minimum just a little bit so I can go below the x-axis and be able to give myself a little bit of room. So I'm going to make this from like negative 50 to positive 500 on the y's graph. And so it'll start at negative 50 down here. That way I give myself a little bit of space down here. Hopefully this is enough. So now when I hit trace, it doesn't block it. Right? So that's a nice little trick there. Okay, so now I needed to choose 2 values. We saw that if we choose the first 2, that line right there is just not going to give us a good approximation of the rest. So we chose the points 9, 249. So this one, 9, 249, and the last one. So we're going to find the line that goes, we found the line that went from here to there. Okay? And we found that line to be equal to a line that has a slope of 36.33 and a y-intercept of negative 77.97. So let's type it in here and graph it. To do that, you go over to y equals, and this is where you graph equations. So like I said, our calculator is not clever enough to be able to change the variables. It's always in terms of x's and y's. And to graph it, you need to solve for y. So you can't just type in any equation you want. It has to already been solved for y, which is why it just has y equals, because that's all it accepts, an equation that starts with y equals. Luckily, we've already done that. So we need to type in 36.33 and then x. X is this button right in here. It has an x, a tau, a theta, an n. So the calculator knows which is which in various, situations. So here it'll know that it's an x. If you're not getting an x when you hit that button, that means that it's in a different mode. So you got to go over to mode and flush everything to the left, particularly where it says function. You got to make sure it says function in there. Okay, so at any rate, let me go back to y equals. Okay, so we got to go over to here, 36.33x. And then now be careful. If I hit this button, it'll probably give me a different answer. This button means negative, but I don't want negative 77. I want a subtraction. It's an operational symbol, so I need to go to a subtraction symbol right there. Minus 77.97. Okay, when you're done with that, now you can hit graph, and there it goes. It's a line that goes through the last two. Keep in mind, the graphics aren't great on this thing, but it's supposed to go through this point and that point. So we first started this chapter by creating a scattergram, right? We created a little scattergram of something. Here it is. This isn't this one with the apple stars, just some random one we got, some scattergram. And the first thing we did is create a model by just eyeballing it, right? We just said, it looks like it kind of does that. So we just created one, right? No equations, no math, just created one. And from that, we were able to make some good guesstimations about where this intercept is or where it's growing. Okay, so there was the eyeballing. Now we learn how to get an equation that will be a good approximation by finding 2 points. So if this scattergram was given to us, our first task would be to create the scattergram and then come up with 2 points such that if I draw the line between those 2 points, it would make a good approximation. So it's sort of a step above just eyeballing a line. When you eyeball it, by the way, it doesn't even have to go through any points. You're just saying it's sort of like right there. It doesn't even have to capture any of the points. But now we're saying, well, let's pick 2 points. And some of them are terrible choices, right? Like if I chose these two, that line would do a terrible job of approximating it. These two would not be good either, right? All the points are above it. That's not good. But maybe, I don't know, how about these two? This one and this one. Maybe that's a great thing. It goes right through the center, some below, some above. That's a good choice. If someone thinks maybe these two are a better choice, some below, some above, that's a good choice too. I don't know that I can really argue that one is better than the other since we have very limited information. So there's lots of good guesses out there. Certainly some bad guesses, right? These two would be a terrible guess. No one could argue that that line right there does a good job of approximating this. Okay, so we picked 2. Maybe I'm going to guess that the best 2 are this one and that one. So I'm going to use this point right there and this point right there. Find the equation of the line and draw it. And then I'll have an actual mathematical equation for the green one. And then that I can use to make good approximations about things and, be able to answer some questions. But now we have an actual equation. and that equation will go through a minimum of 2 points of your actual data, right? Maybe it happens to go through another point, who knows, but at a minimum it should go through the 2 that you chose. Good? Okay, so those are the 2 things we've done now, and then the third thing we're going to do is have our calculator choose the best line. The calculator is going to take all of the points into consideration, and it's going to do this other equation that we're not really going to do by hand. It's going to do something different, and it's going to come up with a line that's sort of an average of all the points. Not just 2 of them, it's going to consider all of them. And it's going to draw a line that comes through all of them. So, for instance, it might, I don't know which color, okay. I mean, maybe the calculator decides that that one is the best fit line. It's called the regression line. So, we eyeball the red one, then we maybe choose 2 points and do all the work by hand. That's how we find the green one. But now we're going to find the regression line, which is like this yellow one there. And there's no arithmetic for us to do by hand. So you just have to learn how to get the calculator to do that, and it'll just give you the answer. Okay, so that's what we're going to do with the Apple one now. So we were given, so back to the Apple one, we were given the table. We were given this table. We converted it into a scattergram. We got this guy. We could just eyeball it and draw a line. Just eyeball it. We could do that. We could also pick 2 points and go, okay, maybe these 2 points would make a good approximation. Come up with all the work to come up with the equation of the line that goes through those 2 points. Graph that line, and then use that equation to be able to answer some stuff. Okay, we could do that. Or we can have the calculator come up with its own approximation called the regression line. So let's go through that process now. Okay, so here's our scattergram, and then this is the line that we created, that we graphed when we used we found the equation connecting this point and that point. So for now, I'm going to deactivate that line. Okay, I just don't want to graph it right now. So I'm going to go over to where it says y equals, and this is where I typed in my answers. Okay, I could clear it, and that would delete it, and that's fine, you could do that. But I know I'm going to use it in a little bit. So I want to deactivate it. That's different from clearing it. To deactivate it, notice how the equal sign is dark right here? That means it's active. So I can use my arrows to go over on top of the equal sign and hit enter, and then the equal sign when I move away is no longer dark. Now it's light. That means that it's been deactivated. It's not going to try and graph it. It's just going to be sitting there so that later I can come back and hit the equal sign, hit enter, make it dark, and then it'll graph it. So it's a good way to save it in my, store it there, but I don't have to graph it right now. Okay, so just do that. All right, now let's get out of here. Let's go back to our main screen. Here it is, our main center screen. Okay, so to get the calculator to give me the best fit line for the scattergram we're dealing with, I'm going to hit stat, the stat button. Then I'm going to go to the right where it says calculate. And I'm going to go down to where it says lin reg ax plus b. Linear regression ax plus b. This is kind of like y equals mx plus b, except instead of an m for slope, they're using a. This a right here represents the slope. I don't know why this company decided they wanted to use ax plus b instead of mx plus b, but that's what it means. Okay? So use your arrows to go down there and then hit enter. Now, some of the older calculators, like this software here, go to this screen. They go back to the main screen, and now they're waiting for some information. They're waiting for you to type in the coordinates of the x coordinates. So I put them on list 1. So I'm going to put parentheses, second L1, comma, second L2, comma, right? So parentheses, which is above the 8, then L1, which is above the 1 in blue, and then comma, which is above the 7, then L2, which is in blue, above the 2, comma, and then here we're going to go to vars, go to the right, enter. This is where you tell it where to store your newfound information. You can store it anywhere you like, except you got to be careful that if you choose, like if we chose y1, it would erase the other equation that's already on there and write over it. And we don't want to do that. So just be careful that you don't accidentally erase something you want to keep. So I'm just going to stick it in y sub 3. There was nothing down there. I don't care about y sub 3, so I can write it there. So you get to there, close parentheses, and then you're going to hit enter. Okay, now some of you guys might get these R things and some of you won't. It doesn't matter. It won't affect us here in this class. So if you got them, great. And if you don't, doesn't matter. But this is what you get. Y equals ax plus b. This is the linear equation where the a, the slope, is 35.2136. And the b is negative 68.67 ... Right? So we have the slope and the y-intercept. And if we hit y equals, it's already been written down here in y sub 3. It's been stored already, right? And it goes to a lot of accuracy, actually. And it's already been active. The equal sign is dark. So I can go ahead and hit graph, and I can graph the dots and the line. So there it goes. That's the calculator's regression line, the line that best fits all those dots. Okay, now one more thing. Let me get out of here. I know that some of you guys are scratching your heads when you hit stat, calculate, and then you go down to lin reg ax plus b, you don't get this. Some of you guys get a new screen that doesn't look like this, and it's a menu that helps you figure out what to type in here. This was like the original software, and then you needed to type it in by hand. Let me do that one more time. So by hand, you needed to know to type in parentheses, L1, comma, L2, comma, and then vars, go to the right, enter, pick where you want to store your information, enter, close parentheses. People didn't like having to do all that. It was confusing, right? So the next generation of calculators came up with a new screen. So when you hit lin reg ax plus b, a new screen pops up, and they just specifically ask you for this information. Where is the x coordinates? Hit L1. Where are the y coordinates? Hit L2. Then it asks you for storage. Storage is where you do this thing with the vars, go to the right, right? So you do that part right there. Vars, go to the right, enter, choose the value you want. And then when you're done, use your arrows to go down where it says calculate and hit enter. There's another thing on there, I think it's called frequency, or there might be some other things. Leave those blank. The only thing you need to type in is x coordinate, y coordinate, and storage. Hit calculate, and it'll take you, it'll give you the same answer. Once you hit calculate, you'll get this. Again, you might get the R value, you might not, it doesn't matter. All we really need is the A and the B, and when we go over here, you'll see that it's there. Okay? While we're on here, we can also go back and activate the old one, the one we got by hand. Hit enter. And now if we graph, we'll see both of them. So there's one and there's the other, and you see they're so similar, it's hard to even tell the difference between them. We can zoom in, and we'll see that they're actually a little bit different, but they're pretty close. Okay, so the equation we found with 2 points was a very good approximation of all the points. But in some cases, you'll see that they're a little bit different. And I would say in most cases, you'll see that there's a slight difference between them. Okay? And once we find that linear regression, now we can answer some questions about our data. We can figure out, for instance, a good approximation of how many Apple stores there were in, say, 2016. So we have 2 ways to do that. We can either use the linear regression equation that the calculator found, or we can use the equation that we found by hand when we wanted to approximate things. So let's use either or both of those to figure out our good approximation of how many Apple stores there were in 2016. Okay, so using the 2 points that we used originally to find a line that approximates the data, we used these 2 points, we used some awesome algebra, and then we found this equation. This was the equation of the line that goes through these 2 points, and we said, based on our graph, this was a pretty good approximation of the data. So now we can use this equation to approximate how many Apple stores there were in 2016. So the first thing we have to do is convert 2016 into a t-value. So what t-value would that be? T is the number of years since?
2000.
2000. So in this case, t is equal to 16. Okay, so we have to submit a equals to 16. So we have to replace that t with a 16. So n equals to 36.33 times 16 minus 77.97. We do the same thing with this one. Now this is the linear regression function that we got from our calculator. No arithmetic needed to be done here. Just push the right buttons, get the answer. This is the calculator's linear equation that best approximates the data using sort of an average of all of them. So it's better, it's superior to this one, except here we got an opportunity to do it by hand. We came up with an approximation using by hand, where here we're using technology, right? So we have to know both skills. So here we're going to do the same thing. We're going to let t equal to 16, and so n equals to 35.21 times 16 minus 68.67. So what do you get in both cases? What do you get in this case?
532.16.
0.16. Okay. And what about over here? What do we get here? Whoa, 494?
Yeah.
Point what?
69.
69. Okay. So they're a little different, right? The equations were very similar. When we graphed them, they looked pretty close. But obviously, even a slight difference does result in a pretty big difference in our result. So which one are we more confident in? Do you think the real answer is closer to, this is maybe approximately, let's round it to the nearest whole store, so 495, or 532? Are we very confident in these? Well,
Both close.
we're sort of close, okay. Are these interpolation or extrapolation? Extra, right? Polation. The last known data value that we have is 2012, is it? Yeah. The last known data value was back from 2012. Lots of stuff could have happened since then. Maybe they slowed down their growth. Maybe they decided, 400 is all we need. They reached that and they stopped making them. Who knows? Maybe they decided, man, we need to put out a lot of these. Maybe they went on a growth spurt and they built a lot of them. Who knows, right? So we're not very confident with this, but just based on the information we have, if we had to make a guess, these are good guesses. This one is better because it includes all of them. All the points are included into this equation, so it's making a better approximation than this one. This one was just the last 2 points, and we visually could see that it was a pretty good guess, but if I had to choose between the two, this one is a little bit better just because it includes more data points in the creation of it, and so maybe it does a better job of predicting things. Okay? So once you guys find out how many Apple stores there really were in 2016, we'll see how close it came. Alright, see you guys tomorrow.